An aircraft weighing tens and sometimes hundreds of tons approaches the runway at speeds exceeding 230 to 270 kilometers per hour. Beneath it lies a runway that, at first glance, seems far too short for that amount of mass and kinetic energy. And yet, just seconds after touchdown, this massive machine comes to a complete stop. That naturally raises a question. How does an airplane actually slow down? And this is where the most common misconception needs to be cleared up right away. An aircraft does not stop the way a car does. Wheel brakes are only one part of a complex, multi-layered system. If an airliner relied on brakes alone, safe landings would simply not be possible. Aircraft braking is a sequential process that begins long before the wheels ever touch the ground. It involves aerodynamics, mechanics, hydraulics, electronics, flight crew calculations, and even weather conditions, all working together. Each element comes into play at a very specific moment, and an error at any stage can increase the landing distance by hundreds of meters. Preparation for stopping starts during the final approach. Pilots calculate approach speed, descent angle, wing configuration, wind direction and strength, as well as runway conditions, whether it is dry, wet, or contaminated with snow. This is critical because even a small excess in landing speed can significantly reduce braking effectiveness later on. The first tool used to slow the aircraft is aerodynamics. If you're interested in understanding how complex machines actually work beyond simplified myths, this is exactly what we focus on. During the approach, pilots deploy the flaps. These movable wing surfaces increase lift at low speeds, allowing the aircraft to descend in a controlled manner without stalling. But there is a trade-off. Flaps dramatically increase aerodynamic drag. In effect, the aircraft begins shedding speed while still in the air, long before touching the runway. As a result, it reaches the ground at the lowest possible speed that is still safe, which is crucial for everything that follows. Flaps are not simply extended wings. Modern airliners use multiple flap settings, each designed for a specific phase of flight. The configuration is chosen to ensure the aircraft crosses the runway threshold at a carefully calculated speed. The lower the speed at touchdown, the shorter the stopping distance, and the lower the loads placed on all subsequent braking systems. The moment the wheels touch the ground marks the start of the second phase of deceleration. At that instant, the wheels are not yet spinning at aircraft speed. Within fractions of a second, they accelerate from a complete standstill to full rotational speed, entering an extreme operating regime and experiencing enormous loads. Aircraft tires are engineered to withstand immense weight, very high temperatures, and severe stress. That is why aircraft wheels are typically filled with nitrogen rather than regular air. Nitrogen reduces the risk of overheating and ignition during intense braking, and this choice is far from accidental. Almost immediately after touchdown, either automatically or by crew command, spoilers deploy on the upper surface of the wings. Their primary function is not to slow the aircraft directly, but to destroy lift. As long as the wing continues to generate lift, part of the aircraft's weight remains effectively off the wheels, reducing braking efficiency. Spoilers force the aircraft firmly onto the runway, transferring maximum load to the landing gear and setting the stage for the next phase of braking. Only after all of this do the main deceleration systems fully take over, wheel brakes and engine thrust reversers. But by that point, the aircraft has already dissipated a significant portion of its energy, because the stopping process began long before touchdown and was carefully orchestrated down to the second. Once the aircraft has been firmly pressed onto the runway and the aerodynamic phase has done its job, the process moves into pure mechanical braking, the harshest and most energy-intensive part of the entire stop. The main workload is carried by the wheel brakes. On modern airliners, these aren't simple pads like on a car, but multi-disc brake assemblies, most commonly made from carbon composites. They can absorb enormous amounts of energy. During a heavy jet landing, we're talking about hundreds of megajoules. In other words, a huge portion of the aircraft's kinetic energy is converted into heat in just a few seconds. After hard braking, brake temperatures can exceed 1,000 degrees Celsius. That's why, after landing, an aircraft may sometimes have to remain stopped while the brakes cool down. Taking off with overheated brakes is dangerous. Excessive heat can cause damage and increases the risk of fire in the landing gear area. For that reason, brake temperature is continuously monitored in the cockpit, and decisions about taxi and further operation are made strictly by procedure. And here's the problem. No human can precisely modulate braking force under these conditions. That's why aircraft use an automatic braking system, auto brake. The crew selects a mode, from minimum to maximum, and the system computes the required brake pressure based on speed, aircraft mass, and runway conditions. The goal isn't maximum braking at any cost, but predictable deceleration with stable controllability and a safe margin in runway distance. On top of that, there's an anti-skid system, similar in principle to automotive ABS, but far more sensitive. It monitors the rotation of each wheel and instantly reduces brake pressure if there's a risk of locking up. Even a brief skid at landing speed can lead to loss of control or tire damage. Thrust reversers matter too, but they're often misunderstood. Reverse thrust is not the primary braking method. Its purpose is to dump a significant amount of speed in the first seconds after touchdown, while the aircraft is still moving fast. On a dry runway, reversers can contribute up to about a third of the deceleration early in the roll, but their contribution drops quickly as speed decreases, and the brakes take over. On contaminated or slippery runways, reversers become especially valuable because they don't depend on tire-to-runway friction and remain effective even when traction is reduced. The runway itself is also an active part of the stopping system. It's not just asphalt or concrete, but a surface engineered with specific texture, slope, and drainage. Water must be removed quickly, otherwise you can get hydroplaning, where the tires lose contact with the surface. That's why, in heavy rain, required landing distance can increase dramatically. And if something still doesn't go to plan, some runways include an emergency stopping area at the end. The most well-known example is EMAS, a bed of crushable engineered blocks. An aircraft essentially sinks into it and loses speed rapidly without structural destruction. It's a last resort solution, but it has already saved dozens of crews and passengers. The key point is this: aircraft braking isn't one mechanism, it's a system. Every element supports the others. If one becomes less effective because of conditions, the rest compensate. That layered redundancy is exactly what makes the process so safe. So an aircraft doesn't stop because it has powerful brakes. It stops because of a carefully calculated scenario in which aerodynamics, electronics, mechanics, and the runway itself all work together. It's not a single hard stop. It's controlled dissipation of massive energy, step by step, with no room for mistakes. Braking is a complex process where every detail has a purpose.